So, welcome everyone. Let's have a look at problem 18.2. This problem we are supposed to write down the LMIs that compute the H infinity norm and the H2 norm. The system using conditions 18.22 and 18.19, which I will shortly review as well. So the task is to be completed using LMI lab, and the code for this is already there, but I will consider using CVX. Both are basically linear matrix inequality parsers, and both of them eventually call the SDPT or Zadumi optimizers to do the job, but I find the CVX parser much more user friendly. But I mean, we encourage you to try both. In this exercise I will demonstrate using CVX. Once we do that, we have to verify the results by using the norm command in MATLAB. So let's try to review the LMIs first. We are given T of S, a transfer function, and we need to find the H infinity norm and the H2 norm with linear matrix inequalities. So let's first look at the H infinity norm. The LMI for H infinity norm looks something like this. If there exists a P, a positive definite, and a gamma, positive definite, positive, such that A transpose P plus PA, PB, C transpose T transpose C T minus gamma I P transpose P. This matrix is negative definite, then we have that the H infinity norm is less than or equal to gamma. So that is the LMI that we have. Now the core idea, let's also quickly review the core idea behind this LMI. So basically, if this LMI, so let's call this f of p comma gamma. So the core idea is this: if there exists a p positive definite and a gamma positive such that f of p comma gamma is negative definite, then that means that there exists a function v of t such that defined as, and this will be positive definite because p is positive definite, and this will be 0 only when x is 0, and we will also have v dot of t plus y transpose of t y of t less than or equal to gamma squared. u transpose of t u of t for all times. So this LMI, which is this condition, ensures that there exists a function v of t such that its derivative plus y of t transpose y of t is less than or equal to gamma squared times this, and then we just need to integrate both sides to obtain. So y transpose y is just the norm of y squared plus v at infinity minus v at 0 is less than gamma squared Now note that H infinity norm is only defined for stable systems, and for stable systems this should go to 0, and we consider 0 initial conditions, so that should also vanish. Moreover, because of this LMI, we also indirectly ensure stability because we have A transpose P plus PA in the 1 1 block, and for this matrix f of p comma gamma to be negative definite, the 1 1 block also has to be negative definite. So v of infinity would be 0 because of stability, and what we have then is basically the L2 norm of y squared is less than gamma squared times the L2 norm of u, and we know that the H infinity norm is the induced L2 norm, and so we have clearly that T of S H infinity has to be less than gamma. So that's the core idea in this LMI. So once we have this linear matrix inequality, we can solve the following optimization problem. Minimize gamma subject to p positive definite and f of p comma gamma negative definite. And now here f of p comma gamma is not homogeneous because we don't have p in these terms, so we write down the same problem by first fixing some tolerance a problem like this. So we will now solve this using CVX. So let me bring here the code. So this MATLAB function here takes in as input the A, B, C, D matrices and the tolerance, and gives out the H infinity norm and the P that was found in the LMIs. So so this is just calculations of different sizes, so size of the states, so that's order, that's number of inputs, that's number of outputs. We start with the CVX environment. Here we define this as a semi-definite programming problem. Then we define the P as an n by n symmetric matrix. We define another variable called gamma hinf, which we will then minimize subject to two constraints. One is P being greater than or equal to tolerance of identity, so this is the relaxed version of P positive definite, and this one is the relaxed version of f of p comma gamma negative definite. Note that f is defined here symbolically because p and gamma hinf are variables, and then we return the hinf norm and the p. Yeah, and that's it. Thanks a lot. Now we look at the H2 problem. So again, we are given a transfer function t of s, and we need to find the H2 norm with linear matrix inequalities. So the LMI for computing the H2 norm looks something like this. If there exists a new positive and a P positive definite matrix P such that ATP plus PA plus PB transposed is negative definite, and trace of CPC transposed is less than nu, then we have that the H2 norm squared is less than nu. So again, like we did for the H infinity case, let's quickly review the idea at the core. So we know that the H2 norm has an interpretation in the sense of the impulse response, in that it is the and the impulse response can be written as this. Now we can imagine that if we substitute for, so let me just delete this H2 norm and say G of S H2. So we can imagine that if we substitute for G this quantity, we will get back something like C controllability gradient C transposed, and this we get because the controllability gradient is you can clearly see that if we substitute this here, we get the controllability gradient inside this and the Frobenius norm of a matrix, or of a let's say of a matrix, is given by trace of A transpose A. So with these three ingredients, you can see that the H2 norm first of all can be written as the square root of trace CWC C transposed, and now you also know that the controllability gradient can be found out by solving the Lyapunov equation, because the controllability gradient is the unique solution to this equation. Now we can very similarly do it the other way around by using the property that trace of AB is trace of BA for square matrices, that the H2 norm can be written in the form of observability gradient as this, and the observability gradient can then be found as the unique solution to a different Lyapunov equation written here. Now the idea to go to the H2 norm LMI is as follows. So if there exists a P positive definite such that ATP plus PA plus PP transposed is negative definite, then clearly there exists a Q which I can decompose as P tilde B tilde transposed, because it's positive definite, which satisfies this equation. Now this can be written as so the P that we found here is basically the controllability gradient of an extended system So if the original system, what was it, is G, so if the original system G, then this P that we found here, so that satisfies this LMI, is the controllability gradient of a system GE, of an extended system GE, where GE is then the original G and this B tilde. So this is with an additional input, and now clearly the H2 norm. So, and now you can show that the H2 norm of GE, the H2 norm squared, is given by trace of CP transposed is then greater than the H2 norm squared of G, because what you have in GE is just an additional channel, and you can try to show this by using the definition. So we have that is less than the trace of CP transposed, and if this is less than nu squared, then we also have that the H2 norm of G is less than nu squared. So that's the core idea behind this LMI. And now let's look at the code. So this function, this MATLAB function, takes in as input A, B, C, D and the tolerance, and gives out the P, and that is the variable in the LMI, and the H2 norm. So first again we compute the sizes, then we define P as a symmetric n by n matrix. We define the problem as a semi-definite program like we did before. Then we define the H2 norm squared variable, so that's nothing but the nu squared, or the new variable, and then we just write down the relaxed versions of P positive definite. So this you need not write down, you can remove this one, it should still work. And then we have TP plus PA plus PB transposed, negative definite and the relaxed version of this one, and then the trace being less than nu squared, and then we return the square root of nu squared as the H2 norm. Yes, and I think that's it for this problem. Thanks a lot.